starting off, I know I'm starting a minute early, but everyone's here, so I figure let's use the time wisely. First, I apologize. I decided I'm not taking the blame. The first homework assignment, I took the blame. I said, put assignment on, and apparently I didn't read it carefully, and it was from the wrong section, even though it said. This time, I know they're not the questions I assigned. Right? When you looked at the homework assignment, it had all of these problems that were stuff we haven't covered. Stuff that we're going to cover within a week, but we haven't covered it yet. And I went to look at it, and I looked at my future assignments. You probably haven't looked. I hope you haven't. I changed all of those because it had, like, for the 151 students, it had problems that said it's algebra based from this section, but when you look at the problem, it was calculus from a different section. And I am quite certain I didn't assign calculus problems to the Physics 151 class. So they made some updates to the homework system between when I made the assignments and when class started, and I think that change must have changed the problems. So anyway, I apologize. I just deleted the 4 problems that were in the wrong section and left 1. And, well, you say thank you for some of you, but for some of you it was highly distressing. Like, I worked really hard. I had no idea how to do these, or, thank goodness I had high school, whatever, and then, wait, it's gone after all that work? I apologize. I didn't mean to cause the stress. Just a reminder, the last type of assignment, not counting the scrapbook and tests, will be first due on Tuesday, and that's the pre-lab quiz. Before you come to lab on Tuesday, make sure that you go to Moodle and you complete that pre-lab quiz, which is questions based on the lab. You should all have your lab guides now, right? And it's open book with the lab guide. So you can just flip through and all the answers should be boldly stated. Mary, you want to just show that so people, if they don't have it, they know what it looks like? It looks like that. Make sure you do write your name on it. Every now and then we'll have students that leave theirs and then we have a problem. Yeah. It's due 5 minutes before the start of lab, so it's due at 1:55 p.m. tomorrow. It's open book. You only have one chance at it, so you want to do good on it. And remember, it's a personal quiz, not a group quiz, so it's inappropriate to, let's just take Nathan as an example. For Nathan to say, hey, Leslie, did you get this question on your quiz? Oh, great. What was the answer? Right? That would not be honest. That would be dishonest. Any questions about the pre-lab quiz, the homework? Okay, then it's time to look at a homework problem. It was really hard for me to decide which one of the 1 homework problems that I was going to have you do, but I settled on the 1. And got to not look at these. Watch, it'll probably be funny and come up with the one that's already done it. The group that's going to come up now is, indeed, it came up with the ones that already did it. Well, next try. Hannah Armstrong, Max Miller, and Clayton Rossi. Come on up, and for each one of these, say yes or no and give your reasons why, and cross them out or circle them as appropriate using this stylus. I know this is kind of a toughie, but what are you going to do? It's the only option I have.
Okay, so for part A, the only one that's scalar is time because it's only magnitude. You don't need direction.
Can you do that?
So everyone just make sure you're clear. They circled time. That's the only one that's not correct. Or that's a scalar rather than a vector. Can we get down? Oh, no, it says scalar. Excuse me. It's the only one that is correct.
Yeah.
So for part B, we put this one because a vector is magnitude and direction, not the other ones.
Now, because a lot of students still ask me this question 2-3 months in, what does magnitude mean?
Huh? I'm sorry.
Because a lot of students still ask me like 2-3 months into class, what does magnitude mean? What is the word magnitude? What does it convey?
Is it magnitude speed?
No,
No.
it's like the number, like the measurement, like 11 meters or
It's the number, It's the size value.
Yeah.
Size value.
Just want to make sure that's clear so people are, well, I learned this is the definition, but don't know what it means.
And the vector quantity would be displacement, 5.
Yeah, because you need a magnitude and the direction that it was displaced.
Okay. That was it. Any questions for the fine folk there? That was nice and quick. By the way, I was thinking about this. I am not normally going to do this, but because our first week was a little shortened and we had at least one group there that didn't realize on the second day, we have to raise our hand if we want to get the extra credit. I'm going to only take new groups for this week. Remember I said that I would restart every week. So in theory, the group that just presented and the other group that has the extra credit for the end of the class would be available again for today. I'm going to, at least for this week, keep it. Those two can't do it, so other groups can have better chances. And then we'll do every week you have a chance after that. All righty. Now that we have finished a problem, let us, get in with our presentation. Here's a graph looking at motion that we talked about at the end of last class period. This was, let's just try to describe what's going on with these graphs. If you look at the leftmost graph, what do you have going on for the first half of the graph?
Moving a distance away from a point.
Okay, we're moving some distance away from the starting point. Notice the vertical axis is position. And so the position is increasing as time increases. The goal of tomorrow's lab, the purpose that you'll have to write down, will be to understand how to interpret these kinds of graphs. So I'm going to introduce it here, and then in lab tomorrow, you're going to be walking back and forth, making measurements of your motion and interpreting, okay, so if I do this, that's what it looks like. So here we have something that the position is getting farther away as time goes up. And what shape do we call this line? It's very simple, almost rhetorical, but not. You ever seen a Google car? Well, you can't now.
Oh, yeah, that was cool.
Unfortunately, we didn't have time to go stand in the window, and but then they would have blurred us out anyway for privacy reasons. Anyway, that's the first time I've ever seen a Google car before. Yes, well, the back of your head will be in Google Street View probably in a month.
Nice.
Yeah. Okay. So, that was just something odd. So this is a straight line. I heard people say that as I interrupted you. Oh, well, now it just went that way back up to the parking lot. They got to cover every road, and I guess our parking lot counts as a road for today. I don't think we're going to see them again. Okay. I'm sorry, I am a disruptive force. ADD is strong in me. It's a straight line relationship or a linear relationship. So here we have speed increasing linearly with time. If I were to make an equation for this line, what would that equation look like? Okay, y equals mx plus b is the equation for a straight line. Now we have learned, if we look at what's on these axes, what's on the vertical axis? This is going to be its position with the variable x. So this is going to be confusing. I'm going to, with all of my might, try to change the color of the pen and still have everything work. Yay. So what was in the y position is now x because that's our variable for position equals, and I'm going to leave blank for the m, and in the place of x, we have whatever's on the horizontal axis, time. So that's rewriting the equation based on what I have on my vertical and horizontal axes. And so whatever is missing is the slope. But we have learned a relationship between position and time, that is that the speed or velocity, for these graphs here, I'm going to go ahead and say the word velocity. Because these graphs, we have a one-dimensional motion where forward is positive and backward is negative. And so it's actually a vector in one dimension. And so velocity is appropriate to use here. Positive velocity means going forward, negative velocity means going backward. So in this case, the velocity, and of course, I really have to put vector signs if I use the word velocity, is the change in position over change in time. So if I solve that for the final position, there's taking that same equation and solving it for the final position. Now, we just don't like to put the subscript F for final. We just put X at whatever, thank you very much, X at whatever time I'm going to check. And likewise, we often don't put the delta T. We just put T with the understanding that time was 0 when I started. And time is T when I check V. So we usually write the equation like this. X is equal to X initial plus VT. Now, if I compare this equation with this equation, you say, well, ignoring the difference in having the vector sign and not having the vector sign, those are the same equation. What is multiplied by time? In this equation, time is multiplied by this equation. What's time multiplied by? Velocity. And so in the lower equation, I'll just put V there. And then the y-intercept, what is the y-intercept going to correspond to with these equations? If the two equations are the same equation. It's going to be, the y-intercept is the initial position. So the equation for a straight line is the equation that we got from having a constant velocity. And in fact, the slope of that line, how do you find the slope of a line on a graph? We all learned blank over blank. Rise over run. So if I look at this graph and I find the slope, here's the rise, here's the run. The run is the change in the horizontal axis, which would be the change in time. The rise is the change in the vertical axis, which is the change in position. So the slope is delta x over delta t. And what do we call delta x over delta t? Okay. The velocity if it's a vector, the speed if it's a scalar. So the slope of the line is actually telling us the speed. And of course, if we have direction, then we get that from other things. You know, the fact it's one dimension. So I can look at that and say, aha, it has a speed that's equal to the slope. So if I find 2 points on that and find the slope, I know the speed. Now we get to the halfway point, and what happens to this line? It was getting farther away. What happens when we get to the halfway point? It starts getting closer again. What changes about the velocity? Well, from the first half to the second half. So on the way back. Okay, the velocity changes its direction. It becomes negative. This has a negative slope because the downward slope is negative. this had a positive slope because an upward slope was positive. So the direction of the velocity changed. If you actually calculate the slope, you can tell by the symmetry, it has the same magnitude slope, just one's positive, one's negative. So the second graph here, velocity versus time, has a positive velocity to the halfway point, then a negative velocity for the rest. But the speed, why does the speed not look like the velocity graph? The speed is just the okay, magnitude is the word I was looking for. There's other answers you could get, but it's just the magnitude. That the magnitude stayed the same, the number, the size of it. All that changed was the direction. And so that's why this stays the same. Those graphs make sense?
So speed versus time is based on the magnitude? Does that make sense?
The speed, this axis right here, is the magnitude of the slope. That's correct. Emily?
Can you explain the velocity versus time more?
This graph here? Okay, we have the velocity. So this first half corresponds to a positive slope. And so that's a positive velocity because the slope is positive. The second half has a negative slope, and so a negative value. So the slope of the red line is giving us the green line.
And like that straight vertical line is corresponding to the peak of the one on the left.
Okay, so that straight vertical line is non-realistic because if we look at velocity, if I take the velocity versus time graph, I can find the acceleration from that. What's the relationship between velocity and acceleration? Acceleration equals the change in velocity over the change in time. So here, if I have velocity on the vertical axis and time on the horizontal, the slope of a line on that graph is acceleration. The slope is delta V over delta T, acceleration. So I can look at this one, I can say from 0 to 2.5 or 0 to 0.25 seconds, it has a slope of 0, so the acceleration is 0. And from 2.5 seconds to 0.5 seconds, it has a slope of 0, the acceleration is 0. But at 2.5 seconds, what's the slope? The rise is 24, excuse me. The rise is 24 and the run is 0. 24 divided by 0 is infinite. Well, you can't have an infinite acceleration. So it's non-physical. It's not something that's actually possible. But it would represent an infinite acceleration. Question?
But in all reality, if we were to test it, it would have like some type of like.
In all reality, it would have something that's going like this. And there would never be a part that's truly vertical. It looks kind of vertical on part of it, and it wouldn't have anything that's truly vertical because that would represent not real. Okay, one more thing on this graph before I go to the next one. I just talked about how I could find the acceleration from the velocity graph and how I could find the velocity from the position graph. So that means I should be able to find the acceleration from the position graph. What would indicate a change in velocity on the position graph? A change in slope. So if I have a change in slope, I'm going to have an acceleration if I'm looking at the position graph. Now, we don't have the clickers, but that's what this question was. Where do you have acceleration in this graph? And DJ told us it's where you have a change in slope. So the slope is changing in this region. Is it getting steeper or less steep? Steeper. So that means we have a positive acceleration there. And then from here to here, it's changing again. Steeper or less steep? Less steep. So that's a negative acceleration there. And what about this region where it's a straight line? Acceleration is 0. No accelerations, I heard. So here are the velocity and acceleration graphs that go with that line. So we had the velocity was increasing, constant when it was flat, and then decreasing. And taking these slopes, you could get the acceleration versus time graph. Do graphs make sense? In physics, we use graphs a lot. Data tables are great. They give you a good glance factor, but the graphs are even better because they have a better glance factor. You look at the graph, if you know what's on the axes and you know why the graphs were made. Now, these titles here are very lame. The only reason we have these lame titles is because the true purpose here is for you to be able to read a position versus time graph or velocity versus time graph. If we know those things, we can figure out what's going on real quick. Question?
So, whenever it's below the zero, is it because it's in the opposite direction, or?
Okay, acceleration negative means that the acceleration is in this direction. Just like if velocity was negative, that would mean the motion is in this direction. All right, kinematic equations. Yes, James.
I was just curious, for position versus time, is there any way to graph it if it's three-dimensional?
Three-dimensional?
Positional,
Yeah. Not conveniently that I know of.
I mean, I know computers can make use of it.
Yeah, not that I'm aware of. Okay, kinematic equations are the equations that describe motion. Now, for everyone who is in Physics 151, everything we do in physics class will have a constant acceleration. The acceleration may change from this constant value to this constant value, but you're not going to have a changing acceleration. In that case, for constant acceleration, then these are the equations that describe all the motion. At the top, I have the definitions of average speed and average velocity. And then I have just the definition of what average is. Initial plus final divided by 2 if you have a constant acceleration. That's only going to be correct if it's a constant acceleration. So remember, the equations we're doing are for constant acceleration. You don't need to get uptight about it. I just want you to know that so that, if you come into a real life situation where acceleration is changing, hey, that's a little different. If you combine these equations, you can come up with the equations down below. Or if you know calculus, it's easier to get the equations down below, or at least more straightforward. I'm not going to spend the time to derive these equations, but the ones down below are super, super important. These equations here. So looking at these equations, the top equation relates position with the average speed and the time. Notice that's average speed. So if the speed is changing, it's really not going to be a correct equation. So you need to have constant speed really to use that. Constant speed tells you the acceleration is a value of 0. In fact, if you look down below, this equation and this equation are the same thing if acceleration is 0. But that lower equation, this one here, has all of our kinematic variables: position, velocity, acceleration, time. Those are kinematic variables. And that one has all of them. We use that one probably 90% of the time in our problem solving for kinematic equations. So that one you're going to be really familiar with. The one that's above the circled equation doesn't have position in it. If you're asked something about changing velocity or speed, you don't know the position, nor do you care about the position, that's the go-to equation. The bottom one is the more complicated equation. It doesn't have time, and it has the squared speeds. If you don't know the time and you don't care about the time, that's the go-to equation. So there's different reasons for these equations. Now, this is probably the first time I mentioned it, but when it comes exam time, I will be giving you all of the basic equations you need. So all of these equations will be on the exam. You don't have to have them memorized. But it won't tell you how to use it. It won't tell you what the variable names mean. So you need to recognize the equations and know how to use them. So let's practice recognize the equations and knowing how to use them. So first, a ball moving. We have here a gentleman who throws a ball. The left picture, he throws the ball up. The right picture, he throws it down. In both cases, he throws it with an initial speed of 13 meters per second. I said initial speed of 13 meters per second, and I did not make a mistake. If you look there, it has V0 equals 13 meters per second on one and minus 13 meters per second on the other. Why is the minus sign there when I didn't say it? Direction. They're really indicating vectors here. Now, technically, if you're printing, you can just use a bold font and it represents a vector. I look at that and I don't see it as a bold font. But I'm not going to go sue anybody or make a big deal. I just know that means that it's going down. I can take this information and I can make equations for the speed at any time and the position at any time. For the speed at any time, I don't care about the position, so I'm going to use the equation without position. So, and I said speed, I'm going to mean velocity here. So the velocity at any time is equal to the initial velocity plus the acceleration multiplied by the time that has passed. Now comes something that's important to know. Once again, this value will be given to you, but no description. If I have an object that's in free fall, that means there's nothing touching it. It's going to fall with a constant acceleration that we call g, the acceleration of gravity. So as soon as this leaves my hand, no matter how I throw it, it's going to have a constant acceleration downward of g. And so my acceleration in this case is given right here. Acceleration is minus. Now, our textbook uses 9.81 meters per second squared. I believe they put the 1 there in the last digit because it makes it clear, yes, this has 3 significant digits. I usually use 9.80 meters per second squared. And that's a non-vector quantity. G, the scalar acceleration of gravity, is 9.80 meters per second squared. G, the vector quantity, is 9.80 meters per second squared down. In fact, we define down as the direction that an object's going to fall. So that's a definition. G is always pointing down. So that equation will tell me the speed at any time. Well, the velocity at any time, because it'll tell me the direction as well. Positive, up. Convention, it says that up is positive, down is negative. And if I want the displacement, that equation will tell me the displacement at any moment in time. So I can go through and I can calculate, how long it took to get to 8.10 meters by taking this equation and saying the x final is 8.10 meters, positive for the direction. X initial is 0. V initial is 13 meters per second. A is minus 9.80 meters per second squared. Put those in and solve it for time. Let us go through and answer some questions. What is the maximum height? By the way, notice I have a subscript y here. Another convention is if we have two-dimensional motion, we use x for horizontal, y for vertical. So that's why I put y there. What's the maximum height? This is going to require us to have a strategy. How could I find the maximum height? Can anybody give me a condition that occurs at the maximum height?
Acceleration is 0. Or
The velocity is 0. And what James said, now in his case, he just misspoke. But it's a very, very common misconception people have. What he said they actually believe. Right? He corrected himself, so that's why I said he misspoke. When you get to the top, the velocity is momentarily 0. How do I know that? Well, it was going up. Now it's going down. Up was positive, down is negative. What number comes between positive and negative? 0. So the velocity has to be 0 at the peak. Well, what about the acceleration? Now, I know I did just say, before I asked that question, that when I have an object in free fall, when nothing's touching it, it has a constant acceleration downward of 9.80 meters per second squared. So you can answer that, well, based on that statement, it's going to have a downward acceleration of 9.80 meters per second squared, but it may not seem right to you because it's stationary. So try this one on for size. If it had 0 velocity, so it's up here in stationary, and the acceleration is 0, what does it mean for the acceleration to be 0? What does that mean? Acceleration is delta blank over delta blank.
Change of direction.
It's
Speed is constant.
It's the change in speed over change in time. So the speed is constant if the acceleration is 0. So if the speed is 0 and it's constant, what's the ball going to do? It's going to stay right there. If the acceleration was 0 at the top, the ball would just stay at the top and never come back down. So that's a good logical way to say, yeah, by just the definitions of speed and acceleration, it can't have a 0 acceleration at the top, even though it momentarily has a velocity of 0. So I know that up here at the top, v top is equal to 0. You don't have to put a vector sign or units when it's equal to 0. So v top is equal to 0. So now I have the initial elevation, the initial speed, the acceleration, the final velocity, initial velocity, final velocity. I am looking for the maximum height. There's one variable that I didn't say in all of that. What was that one variable? Okay, I know. You're like, wait a minute. He just said a bunch of stuff. I didn't pay attention to which ones he said. We know the initial height. We know the final velocity. We know the initial velocity. We know the acceleration. So we have Vxa. What variable did we not have and not care about for the first question? The time. So I'm going to look at the equation that doesn't have time and say, can I solve it with this? Okay, I'm going to hide this now just so in 5 minutes or whatever. If I look at this, I say, well, sure I can. I'm looking for this value. This one's 0. This one here is 0. So my maximum height is going to occur at (13 squared over 2 times 9.8). Someone want to calculate that for us? You have a question, Leslie?
Oh, no, I'm just.
13 squared is 169. 9.8 times 2 is 19.6, but 8.62? Okay, so we get you said 8.62?
Yes.
Now, how many significant digits do I have in that answer? 2. So I'm going to erase the 2. Always calculate it. Always keep all the digits you have until the end of the problem. But then when I report my answer, I'm going to report it with correct significant digits. So there we found the maximum height. What's the speed at each designated height? Well, in that case, I would go with this same equation again. I would be looking for the v. So if I take this equation again, the bottom one, it doesn't ask for times, it asks for heights. I would just put in the different x's and solve it for v. I'm not going to do it because of time, but it's pretty simple. How tall is the cliff if it hits the ground 10 seconds after it's thrown upward? Well, for space purposes, I'm going to go to here where the students answered the questions. We had the initial velocity. I'm going to drop the vector signs. Uh-oh, I forgot. What did the question ask?
For 10 seconds.
Oh, 10 seconds.
Yeah.
So that was time, not. So if time final is 10 seconds, what's the height of the cliff? So now I look at this and I look at my variables. Speed, yep. Acceleration, yep. Height, yep. I'm looking for y final. Now remember, I shifted from x to y. Y is just for vertical distance. X was for horizontal distance. So the same equation is going to work. I look at these variables and I say, well, I'm going to use the equation that has all of these variables. So the equation that has all the variables will be so I'll just put in my values. Well, actually, I can shift over with this one. So I end up with y final is minus 360 meters. That is, the bottom of the cliff is 360 meters below the starting point. And so I've now calculated the height of the cliff. Now, just for the math there, 13 times 10 is obviously 130. 10 squared is 100. 9.8 divided by 2 is 4.9. So 4.9 times 100, it wasn't something complicated. Does everybody see how I went through the calculation? Emily?
Will we have calculator?
You can have a calculator, yes.
Do you have any rules on which calculators we can have?
I don't. I know that it's easy for people to do things that are dishonest with some calculators, but I have a certain amount of faith in my students. So I trust that they will not be doing those improper things. All right, problem-solving techniques. How do you solve problems? Step number 1 is to draw yourself a picture. Now, what I've been doing, I already had a picture, so I didn't have to draw it. So draw a physical picture so you can see what's going on. After you've drawn that picture, list what you're given and what you're looking for. So my picture was already drawn, but then I listed, as you saw what I just finished doing, I listed the values that I knew already, and then I wrote the one I was looking for. Then we're going to decide, I already said it, yeah. Identify what needs to be determined the problem. And then we want to find the equation that's going to work with those variables. This isn't a math class. It's not just put numbers in an equation. But for the beginning of the class, it often looks like that because you're just finding the equation that's going to give you the answer and popping the numbers in. So you find the equation or set of equations that'll help you solve it. You put in your numbers. Make sure your units are right. Did you notice me using units when I did my example? Oftentimes people don't do that because, well, it's inconvenient. But if you put in the units, you can make sure, hey, my units are the same for my answer as they're supposed to be for, a speed or whatever. And it gives you a way of saying, yeah, it's reasonable. Also check the answer to make sure it's a reasonable value. Like, it was 200 miles. Well, probably not. Probably a mistake there. So make sure the answers make sense. So I have 2 problems set out here. We'll just do we can do the first one and then you'll do the second one. So a dragster starts from rest and accelerates at a constant rate of 1.00 g. Now I know that would be the correct way of saying a mass of 1 gram, but here we're using g as an acceleration unit, 9.8 meters per second squared. So it's accelerating 9.8 meters per second squared. How fast is it going after 400 meters? So step one, what was step one? Draw a picture. So my picture starts with a straight line. Believe it or not, that's straight line. And I start with it here, stationary. So I have V initial equals 0. I end with it out here. V final is unknown. I know the acceleration is equal to G. I didn't put the 1.00, just save space. And that's it for me. Isn't it? Oh, no. I have one more thing. X initial is 0. X final is equal to 400 meters. Now I'm done with all the things that are given. So I've drawn a sketch. I've put in all the knowns plus the thing I'm looking for, the V final. Now I need to identify which equation is going to work for me. So I have all the equations listed there. Which one is going to work for this specific question? I'm looking for, oh wait, it doesn't ask me for the time, for the speed, does it? It asks me how, I'll ask for both. First it asks for how fast, and then it asks for how much time. So for the first one, we're asked how fast. I don't have time and I don't care about time. Which equation is going to most likely work for me in that case? The bottom one. So I'm going to take that bottom one and say, there I rearranged it. I solved it for V squared. And then I just put in my values. 0 squared, because it starts from rest, plus 2 times my acceleration is 9.8 meters per second squared, times my distance, 400 meters. So 400 times 2 is 800 times 9.8, which I should be able to do in my head. That'd be what? 8,000 minus 40, no. 8,000, 7,000, yeah, I think 7,600. Is that right? 7,800. Okay, well, you use 9.81. Oh, you use them? So, okay, well, and then I square root that. So square root the 7,800. Now, 88.5 meters per second doesn't mean much to most of us. We just don't know how fast that really is. What units are you used to using for the speed of a car? Miles per hour. So let's convert that to miles per hour real quick. And I'm going to go back to here. We have 88.5 meters per second. And I want to get that into miles per hour. The way I'm going to get into miles per hour is I have to look up a conversion factor. So you should have in the front of your textbook a conversion factor. This isn't the right textbook. Nobody has a physical textbook yet. If you look on your computer, it also has the conversion factors, or somebody can just look up on their phone. 1 meter per second is how many miles per hour?
Meter per second is 2.24 miles.
Okay, so I'm going to put here a conversion factor that has a value of 1, but I need meters per second on bottom. So I'm going to take this and put 1 meter per second on bottom so that my units of meters per second will cancel. And on top, that was 2.24 miles per hour. And so 2.24 over 1 times 88.5 will give me the speed in miles per hour. So what do we get for that speed? It's okay.
98.24.
Okay. We actually only have, I think, 2 significant digits. So really, that would be 200 miles per hour. Do you suppose that's the final speed for a top fuel dragster? No, they're going faster than that after a quarter mile. That 400 meters is the metric quarter mile. Okay, let's go back and, whoops, that was the wrong one. That's my mistake. Throw it to you. Come on. It's going to go there. Oh, yeah. I know why that didn't work. So here's the problem that I have for you guys to work on. The highest vertical leap at the NBA tryouts was by DJ Stevens, who jumped 46 inches. Going to need to convert that into meters. Conversion factor, by definition, 1 inch is equal to 2.54 centimeters. That's a definition. The inch is based on the centimeter. How fast did he leave the ground? And let's just go with how fast did he leave the ground. Okay, so work on it at your tables. I only gave you 5 minutes here, so let's work quickly. DJ, expect the answer.
It doesn't give us time, so.
46 inches, remember, that's about 4 feet. That's a real jump. Remember, if you have an answer, raise your hand. I'll tell you as soon as I find the square root button, I'm just reading the calculator. Yeah.
I'm just kidding. I'm kidding. You're looking for meters, right?
Okay.
Yeah, 4.7 meters. So starting with this.
Okay.
Thank you.
Okay, so this group has finished it, and since we have 1 minute left, they are going to explain it very rapidly.
Very rapidly. So we're using the equation that didn't involve any time, which was the bottom one. And I don't, do you have, let me have that written down. No. So very simply, we simplified the equation. Right. Our displacement was 46 inches. We turned that into meters, converted it to meters, 1.16. This is an unrounded number. Multiplied that by 2 times our acceleration, 9.8 meters per second squared. Came up with, after square rooting our answer to this part right here, we got 4.79 meters per second. I'm sorry. Is that right? That was it? Yeah. That's it. That makes sense.
I did the converting analysis.
Okay, our time is up. Have a great day. I'll see you all tomorrow for lab, if not earlier.